students, welcome back. This is Torres, elbow bump. How are you? Are you doing okay? Is your family okay? Remember, if you need anything, please send me an email so that I can try to help you however I can. So lucky you, you get to hear my voice for another lecture. But the best part is we will be using the Central Limit Theorem to describe the sampling distribution of the sampling means. Yay! The last time we discussed the Central Limit Theorem, we talked specifically on how we can use it to look at sample proportions. We used it to estimate the proportions of the population. And as long as the basic conditions were met, then we could assume that the sampling distribution of our sample proportions is close to a normal distribution. So even if we didn't have skewness values, we weren't able to look at the data visually to determine if we had a normal distribution, we were still able to assume normality based on certain conditions. For the sample proportion, there were three basic conditions. First, the sample had to be random and independent. Second, you had to have a large enough sample, so that meant that the sample had to have at least 10 successes and at least 10 failures. And we also needed to make sure that our population was at least 10 times larger than the sample size. So that's what we did for sample proportions. If all those conditions were met, then we could say that the sampling distribution of the population proportion, or the sampling proportion, was approximately normal. That proportion would act as the center, and we could use this formula to figure out what the standard error would be for the distribution. Once we used the sample proportion and the standard error for that proportion, then we could use that information in order to find probabilities of something being greater than or less than, depending on, what the question was asking. So what we've studied is using the Central Limit Theorem for sampling proportions. Now we're going to start using the Central Limit Theorem for a sampling mean. Just like with proportions, there are a few conditions, but you really only have to check two. The conditions are if a random and independent sample of some amount of observations is selected from a population and the sample size is sufficiently large, then the sampling distribution of that sample will be approximately normal. So what you're going to check for in sampling mean problems is that there is a random and independent sample, a random sample with replacement. The other condition is that the population has to be at least 10 times larger than the sample size. So you're going to check for random and independent sampling, and you're going to check the population condition. You will not have to check the sample condition. The sample size will affect how much error you have in your statistical calculations or your statistical inferences. The standard error will be larger if you have a small sample size, and the standard error will be smaller if you have a large sample size. So as the size of the sample starts to get closer and closer and closer to the size of your population, you're going to get less and less error. Once the size of the sample is the same size as the population, there is no error because the sample population is actually the truth. So that's why a larger sample is always like a benefit, because you're getting closer and closer and closer to the true population parameter. Remember, the population parameter is the truth. All the samples that we're taking are really just inferences. We're trying to guess at the truth as best we can, with the understanding that we may never know what the truth is. So if we select simple random samples of some size sample, then we can model the distribution of these samples with this formula. Remember that big N right here, when it's next to a parentheses, this says that it's normal. So we can check to see if we can assume normality based on the Central Limit Theorem conditions. One, that it's random and independent sample. Two, that the population size is at least 10 times larger than the sample size. If that's true, we can assume normality. Then the population mean is going to be the same mean as for your sample. We're going to take the population standard deviation and divide it by the square root of the sample size. In these situations, if you do not have a standard deviation for your population, you cannot proceed with these calculations. So what are we going to need? You're going to need pencil or pen, whatever you feel best working with, paper, calculator, and some type of technology for probability calculations. I did find some alternatives to StatCrunch that I will link in the description box below. That's just an independent site that has the statistical software that you can use for this. So let's try this with an example. Okay, this one has to do with midwives. So it says approximately 9% of all births in the United States are attended by midwives instead of obstetricians. According to the U.S. Bureau of Labor Statistics, the average salary for a nurse midwife is $108,000 with a standard deviation of $2,500. A random and independent sample of 100 nurse midwives is drawn from this population. What is the probability that the mean salary of the sample is greater than $108,500? Okay, so I've gone ahead and copied that same question here. Just going to read it one more time to familiarize ourselves with this new platform. So it says approximately 9% of all births in the United States are attended by midwives instead of obstetricians. According to the U.S. Bureau of Labor Statistics, the average salary for a nurse midwife is $108,000 with a standard deviation of $2,500. Random and independent sample, 100 nurse midwives is drawn. Okay. All right, so first thing we need to do is let's write a few things out. Well, first of all, we know that our mean for the population is going to be 108,000. And we know that the standard deviation for the population is going to be 2,500. And we know that our sample size is going to be 100. Okay. It doesn't say anything about this being a normal distribution, so we've got to check for the Central Limit Theorem to see if we can assume normality. So first is random and independent. Do I have a random and independent sample? I do. It says right here that it's random and independent. So I'm good to go. Okay, so that is a check. Number 2, I need for my population size to be at least 10 times the size of my sample. So I need there to be at least 10 times 100 midwives in the United States. So as long as there's at least 1,000 midwives in the United States, I'm good. And seeing that 9% of all births in the United States are using midwives, I would hope that there's at least 1,000, because that's a lot of people being born. All right, so I'm going to go ahead and make my normal curve here so that I can start to understand what's happening. And I've got my standard deviations to draw out here. And I've got 0, 1, 2, 3, negative 1, negative 2, negative 3. Those are my z-scores. And since I can assume normality, I can assume that the population mean is right here in the center. So I'm going to try to write this as best as I can. Maybe I can make this a little bit bigger. I'm trying. It's hard to write like a 6-digit number right here. So little. Okay, so now I need to know this distance. This distance is going to be my standard error. I don't have the entire population, so I can't use the standard deviation of the population. I can only use my standard error. And I do have a pretty good sample to go ahead and plug in. So I'm going to go ahead and just scooch this down to show you again what these values were. This was the mean, went right here. The standard deviation for the population is going to go in the numerator, and the square root of my sample size is going to go in my denominator. So let me go ahead and start plugging that in. So here in my numerator, I'm going to have 2,500. And in the denominator, I'm going to have the square root of 100. Okay, so I can bring over my Google calculator now. 2,500 divided by the square root of 100, and I get 250. Makes sense. So my standard error here is 250, which means that this distance right here is 250. So I can just add 250 going in this direction. So I'm going to get 108, 250, 108, 500, 108, 750. And in the opposite direction, I'm going to get 107, 750, 107, 500, and 107, 250. Okay? If you're not sure where these numbers came from, I'll just quickly summarize that since this distance is 250 and this distance is 250 and this distance is 250, then I can just add 250 for each one of the deviations, right? And in the opposite direction, since this is also 250, this is also 250, this is also 250, I can just subtract 250 for each one of those deviations, okay? So this is my model and that I can look at to just get some idea of what's happening. Okay, so the question is, what is the probability that the mean salary of the sample is going to be greater than $108,500? Okay, well, I have it right here. I'm going to go ahead and do, I haven't used that blue color in a while. I really like this turquoise blue color. If you know which color is my favorite to use on Zite Board, comment down below and I will give you extra credit for the first person that pops it in there. All right, so here is 108,500, and everything greater than that is going to be, see, greater than. So the probability of X being greater than 108,500 is what I've just colored right here. So now I can go to StatCrunch. Remember that? I can go to Stat, Calculators, Normal Distribution, and I'm going to put in my information. My mean that I made in the diagram was 108 even. My standard deviation, really what I'm dealing with here is my standard error for my model. I want everything greater than 108,500. And I get that the probability of someone in the sample earning more than $108,500 is approximately 2%. And if I were to write it as a percentage, I would write it like this. As always, I have all the information written out in Google Docs so that you can look at it more carefully. Let's do one more example. This one has to do with trees. There are 8,000 colossal sequoia trees in the Sequoia National Park. The average height of a fully grown sequoia tree is 215 feet with a standard deviation of 25 feet. Now think of it, 215 feet, that's a 21-story building. These things are huge. If you ever get a chance to go to the Sequoia National Park, you need to go. It will blow your mind. It's so beautiful. If a random and independent sample of 50 trees were selected, what is the probability that the mean height of the sample is less than 220 feet? Okay, let's put this into Zite Board. So I'll give you another chance for extra credit and for a comment down below. If you've ever been to Sequoia National Park, tell me what you liked about it. And if you have never been to Sequoia National Park, why don't you Google the size of the biggest trees there? Google the size of the biggest tree there, and I'll give another extra credit to somebody who can tell me the name of the biggest tree there. All right, so it says there are 8,000 colossal sequoia trees in Sequoia National Park. The average height of a fully grown sequoia tree is 215 feet with a standard deviation of 25 feet. If a random and independent sample of 50 trees were selected, what is the probability that the mean height of the sample is less than 220 feet? All right, we got this. All right, let me get going here. So there is nothing in this description in the scenario that says we have a normal distribution. So we need to check for a central limit theorem to see if it applies. So random and independent sample, do we have that? Yep, right here. Random and independent sample, so we can check that off. Green, check. Next thing is we need to make sure that the population is at least bigger than 10 times the sample size. So we need to make sure that n is greater than or equal to 10 times little n. So we know that big N is 8,000. And we know that the sample size is, what size is my sample size? 50 trees. So n equals 50. So we know that 8,000 is greater than 500. So that checks out too. All right, so we're good to go. We can assume that the distribution is normal. Awesome. Let's see what other things I can write down. Well, I know that the mean is 215 feet and the standard deviation is 25 feet. I can draw my model. I'm not trying to be a pain about drawing the model. It's just really good for you. It really puts everything in perspective so that if you've got like a million things going on, you can find if something goes awry. So here I'm going to just quickly draw my standard deviations, my z-scores. Oops, got crazy here. My z-scores. Right, I'm going to scooch this up a little bit. And now I can say that for my average, I've got 215 feet. All right, and I need to find my standard error because this distance is a standard error. I don't have the information for all the sequoias. So, okay, so I've got the standard error for these trees. I can figure out by using the standard deviation of the population divided by the square root of the sample size. So my standard deviation is 25, and I can divide that by the square root of 50 to get my standard error. So let's bring out Google Calculator. You know what I'm going to say? Clear, clear, clear. 25 divided by the square root of 50, and I get 3.5. So this distance right here is 3.5. This distance from here is 3.5. This is 3.5. On the other side, this is 3.5, 3.5, and 3.5. Now I can just start adding things up. So I've got 215. Clear, clear, clear. Let me see if I can scoot this, make this just a little bit smaller so that I can look at my calculations here. Okay, I'm going to try to find all the theoretical raw scores in through here. Awesome. So I got 215 plus 3.5, and I get 218 and a half. And then I'm going to add another 3.5 plus 3.5 equals 222. Just so I don't lose that. Put that right there. I get so excited that I just don't jot things down. Comment below if you do the same thing. 3.5. 225.5. On the other side, I'm going to go ahead and subtract it. So clear, clear, clear. 215 minus 3.5, and I'm going to get 211.5. Minus 3.5, 208. Minus 3.5, 204.5. Yay. Okay, now this says, if a random and independent sample of 50 trees were selected, what is the probability that the mean height of the sample is less than 220 feet? Okay, so I'm going to go back to my favorite blue color here. And where would 220 be? 220 would be right in between 218 and 222. So it'd be like right about here. And this time it says, what is the probability that the mean height will be less? So instead of coloring everything to the right, I've got to color everything to the left. So I need to find what is the probability that is underneath this much of the curve. Gosh, my coloring gets worse and worse. Okay, so what is the probability that the mean will be less than 220, right? 220 feet. Okay, I'm going to go back to StatCrunch. Here's my StatCrunch. I'm going to go ahead and remember, go to Stat, Calculators, Normal, click on it. I'm going to put down that my mean was 215, standard error was 3.5, and I want everything less than 220. Looks like my picture, doesn't it? It's everything from 220 down, and that is approximately 92%. So it's right here, 92%. So I'm going to go back here, and I'm going to say that this is 0.92, and that is the same as 92%. So the probability that the average height of the trees in that 50 tree sample is less than 220 feet is 92%. It's a very good chance that those trees will be less, in the sample will be less than 220 feet tall. Again, go see the sequoias. There's really few things in life that are so beautiful than these giant trees. They're just absolutely incredible. As always, the same information is here. I've gone ahead and written it out in more detail for you, and you can review. Here is a little table that I've created so that you know when you're working with proportions and when you're working with means. Okay? You just want to see what the question is asking you. Is it asking you about a proportion, or is it asking you about a mean? If it's asking you about a proportion, everything in this top row is the information that you need. You need the population proportion, right? That's denoted by P. P hat is the sample proportion. The center is going to be either P or P hat, whichever you have access to. The standard error is going to be calculated using this formula. And remember that you have to have at least 10 successes and 10 failures. For the random and independent sample and the population proportion, you need them for both proportion and mean. For means, mu is the population mean and sigma is the population standard deviation. X bar is the sample mean. The center is going to be mu, the population mean, and you can find the standard error by dividing the population standard deviation by the square root of the sample size. Again, the only conditions that you have to check for in the central limit theorem is that the sample is random and independent, and that the population is at least 10 times larger than the sample size. So what's the big idea? Today's big idea is that if the population is larger than 10 times the sample size, the distribution of the sampling means can be considered to be normal. In order to calculate the standard error for the sample mean, you can use this formula, which is the standard deviation divided by the square root of the sample size. You can only use this if the standard deviation for the population is known. The next big idea is as the size of the sample approaches the size of the population, the standard error statistic decreases. When the size of the sample is the same size as the population, there is no error. The sample standard error statistic will equal the population standard error parameter, so we will actually know the truth. So that's it for today. With that said, don't forget to check your emails, check Blackboard, do your homework, and subscribe to this channel. Even better, hit that notification bell so you know when there are new videos for this course. Okay, this is your teacher Torres saying stay safe, and I will be waiting to give you a virtual elbow bump in the next video. Ciao!